So the point of this video is for you to learn what mass spectroscopy is and hopefully solve some mass spectroscopy problems. I have some sample problems for you to do, and we're going to work through some problems. So before we get into some of the sample problems, I want to have you look at the structure of a mass spectrometer. Now, a mass spectrometer is an instrument, a machine, that can detect different isotopes. Now, one of the premises of the atomic theory is that elements can have different isotopes. They'll have different number of neutrons. So we can see here that the way to do this is by sending the isotope or the atoms through a tube and have them curve. Now, that's all well and good, but in the middle of the curve they have this magnet, and just like a magnet in real life, things are attracted or deflected by the magnet. And so as the different isotopes come down through this curved tube, heavier isotopes will be deflected in different ways. So if it's a really light isotope, okay, that isotope is going to come down and it is going to be really deflected here, and it's going to hit here, okay, like something very light. And then if it's something heavy, then that heavy thing isn't going to want to curve, and it's going to hit the side here. The only ones that make it to the detector, the thing that knows the isotopes, is here, all the way down in the middle. And so if you have an isotope that is just one mass unit away from that isotope, it'll fall here. If it's lighter, if it's one mass unit heavier, it'll turn a little wider. So where it hits on the detector is how we see the mass. And so what you'll do is you will see in the spectra, the output of the instrument, you will see peaks based on where each of these isotopes will hit. All the junk will never not hit the curve in the thing. Okay, so the real heavy things, if there's stuff that's not those isotopes, will hit the side of the tube. Now, this thing is super expensive. Okay, when I was in graduate school, I worked with one that was, in the hundreds of thousands of dollars. If I had to guess, I think it was on the order of $500,000. So it's not like anything that we can get in high school to look at, but and like I said, it works kind of like you would expect. The magnet will cause heavier things to deflect less than lighter ones, and then the ones that are just right will go through the magnet in the curve. So it's the curve and the magnet that help us, and then that's separated by mass. Okay, so as this hits, if a whole bunch hit here and not a lot hit here, you're going to see peaks, and so that's what we have here. Okay, and so this is the mass spectrum of boron. So what happened is, as those boron isotopes were coming through the mass spec, you have some hitting here and then some hitting out here. Now let's talk a little bit about the y and the x axis. Okay, now this relative abundance here relates to how many atoms hit the detector. Now in this case, this is a percentage, 80.1% and 19.9%. It may not be a relative abundance all the time, or a percent abundance. It may be some other value where you set the maximum value to 100. But in this case, it's a percent abundance. And how do I know? Because they add up to 100. Now here, if we're separating by mass, and this is how many were separated, guess what this axis is? Right. This axis is the mass of the ions. And for a boron atom, this peak is at 10 AMU, and this peak is at 11 AMU. Okay, so this becomes kind of a pretty simple, what do I want to say? A pretty simple mass spec. There's only 2 isotopes. And this is how we prove that there are isotopes that naturally occur. Now, naturally occurring isotopes are isotopes that occur in nature. Now, we can make man-make isotopes, but that's not something that we do in this class or talk about very much in this class. This just happens to be the mix of isotopes that boron has. And so what do we get from this? Well, what we do is we get the mass on the periodic table. You just got done with a unit or a section of a unit that talks about mass number versus atomic mass. Well, here what we can do is we can get the data to solve those problems. Okay, so for boron, kind of super straightforward. We have let me draw here. So it's 19.9% of 10 AMU and 80.1% of 11 AMU. And just like we did at the last set of videos, okay, like Tyler DeWitt, I guess I didn't do any of it, but Tyler DeWitt did, and we can do the math here. So 19%, remember when we multiply 10 times 0.199, and when we do that math, we get 1.99, and then 80.1% of 11 is 8.811, and when we add that up, we get 10.801. And when we look at the periodic table, you'll see that the mass, the actual mass in the periodic table of boron is 10.811. And so the reason why this happens is because we are rounding. The atomic mass unit here is not exactly 10 all the time. Okay, it's actually just slightly over 10, and this is just slightly over 11. And so that means that this number is going to be low. And it is, but I think that it makes sense that those two numbers are very close. Only in the 4th sig fig are they off. Okay, so now if we're going to move on, let's see here. We look at zirconium. Okay, now again, this is a relative abundance in percent. How do I know? Because these percentages are all in, these numbers all add up to 100 when we do that math. Okay, so I know that these are in percentages, and then what I also know is that I have to take the percent and multiply it by its mass number, and that's going to give us the atomic mass. So this is 46 point blah blah blah. This is going to equal, when you multiply 11.22%, remember that's going to give you 0.1122 times 91. You get 10.21 blah blah blah. You get 15. When you do this one, 7. If you need help, you can go back and review it. 16.33. Okay, and this one is 2.688. And be careful here with this percentage. You always move the decimal point over 2 places. So this is 0.028. And so when you multiply that by 96, you get this. And then when you add up all of those, you get 91.3184. And again, you compare that to zirconium's actual, and that's 91.224. Compare that, and that's only off by 0.1, 0.1 mass unit. And the reason why that is, again, is because of the rounding that we do. So that's what mass spec gives you. It gives you the data that it allows you to calculate average atomic mass. Now, the thing that may happen is sometimes they may not give you the percentages, okay? Sometimes they'll give you the relative abundance. And so what I did is I blocked out the percentages here, and I said, well, what if they're not given? Well, what if we have it and it's set to, it's just a relative abundance, and what we know is that carbon 12, and look how I'm going to abbreviate that, C12, just like I would, that is set to 100% abundance, and then C13 is actually 1.1 abundance, okay? So what we do here is we have to figure out what the percentages are. Now, that becomes a kind of a straightforward process, just like we would do in a regular math class. What's the total? 101.1. So for carbon 12, okay, we have 100 over the total, 101.1, which is going to equal 98.9%. And then the other one, carbon 13, is we can do or subtract. And if we subtract from 100, we know that that's going to be 1.1%. If we do the math, it works out to be 1.09%. Okay? As soon as we have those percentages, now you can go and do the problem. Okay? So I think it's interesting to do this either way. If you were to do the problem out, and feel free to, okay, when you go out and do the problem out, you'll see that this works out to be about 12.01, okay, as the mass. Okay, so again, mass spec is going to be used to get the data for doing an isotope problem. Okay, here's an element that we don't even know. Now, first thing we have to do, we have to figure out, is this a percent, or is it a is it just a relative amount? Well, if you look at the thing here, they took, whoever published this, took this line and took the top part of it and set it to 100. And then there's two other lines. So because of that, we know that this is not a percentage, but it's just an abundance, a relative number. So what we're going to do, we don't know what element it is. So this is the type of problem that real chemists would get in real life situations, is, well, determine the element from this, okay? And you could do this with all sorts of compounds. You could do this with all sorts of things. You could do it with compounds. One of the surefire ways to figure out residues that they find in crime scenes is to put it into a mass spec. And so as it goes through the mass spec, it'll split it up into different parts of the and you can tell what the residue is from the mass spec, from the mass spectrum. But anyways, we don't know what element it is, but we can figure it out. Okay, well, one of the things we can do is we can kind of guess. We know that the mass is going to be around 20 AMU, and because of the math, we know it's going to be very close to 20 AMU, and it's only going to be a little over 20 AMU. It's not going to be less than 20 AMU. So when we look at the periodic table, we can figure out which one that is closest to, and we can say that neon is probably the answer here. This is webelements.com, a very good website. And so anyways, but neon is 20 plus a little. Sodium, that's almost 23, so we probably won't do that. So anyways, so what element is it? It's probably, I'm going to put in parentheses here, neon, because that's what we think. But just like everything else, we need a little bit of support for that, so we're going to do some math. So, and if you want to try the math, feel free to pause the video. Okay, so we don't know what element is, so we're going to do X, and there's three isotopes, X20, X21, and X22. Okay, now it doesn't even matter if I just kind of guess what the abundances are. Okay, we know that this one is the most abundant, and the most abundant is always set to 100. Okay, it's not percentages, it's 100, so we have to do that extra step. And then 21 is really small. I'm going to say that that's about 2%, or about 2. And this one I'm going to say looks like it's just about as much over the 10 as this one was above the 0. So I'm going to say that that's about 12. So when I add that up, that's 114 total parts. Okay? Now, we do the math, and you go 100 divided by 114. That percentage is 87.7%. 2%. And you do 2 divided by 114. And you have to multiply your percentages by 100. But when you do that, you get 1.754%. And when you do 12 divided by 114, that equals 10.53%. Okay, so now you have the percentages. You take the percentage, multiply by 20, take this percentage, multiply it by 21, take this percentage and multiply by 22, remembering to move your decimal place over 2 spots. 1, 2, 1, 2. So be careful of single-digit percentages. Okay, and when you do that, you'll get that the total mass of all 3 of these isotopes is 20.23, which is very close to, let me see here, which is very close to the 20.18. Why is it off? Again, it's because of the rounding that we do. Okay, so now try it. We can try it yourself. Okay, so we'll go down to this last one here. Okay, so what I did is I made, I covered up the the percentages so that you would guess here. Okay, so I have the abundances. Okay, and I have the isotopes that are present. Now, pause it, see if you can figure out how to do this. Okay, and again, because it's abundances and not percentages, you have to do the extra step. Okay, see if you can pause it and come up with the answer. Now, to do this, again, kind of wacky, but we're going to take all of these 3 and we're going to add them up to get 108.4. And then we're going to do 100 divided by 108.4, this divided by 108.4, and this divided by 108.4. And when you do this, you get 92.25%. So, and that makes sense. Look at this. This is huge. This is 92% of the total number of isotopes that are there. And these 2 are really small. So this is going to be 4.705%. And this one is going to be 3.044%. Now when you do your math from the previous part of the unit, when you take these, multiply them by the mass number, you're going to get 28.107 AMU. Now we have to know which element that is, so we're going to go here, we're going to go to our periodic table, ignore the writing that's here, but we look 28, so okay, so it's 28.085 is silicon, 2731, it's got to be in this case silicon, because silicon is the closest. And again, the reason why it's off is because, or why the values are off is because of rounding errors. So by the end of this, I'm hoping that you understand that mass spec is the way that we understand or realize that there are isotopes in the world, and that you can do the math. It gets you to the math of doing isotope problems. So have a great day, and if you have questions, feel free to ask.